Hello, everybody. Welcome to section 1.9. Welcome to Hogwarts, of course. It's nice to see you all. And we're doing today section 1.9, a very, very famous piece called the Euclidean Algorithm. So let's just get right to it. I'm going to share my screen. I'm not going to video. I'm going to end my video because they say it makes it worse for bandwidth and stuff like that. So I'm going to get rid of my video and I'm going to there we go. Okay. Now the Euclidean algorithm. This is a method for finding the greatest common factor of two or more integers. Right now we're just going to do two integers. Greatest common factor, as you know, is the biggest number that goes into two other numbers. For example, let's just go to I want to go to the Google Doc now. The greatest common factor of the GCF, this is how we would write it. The GCF of, let's say, 12 and 8, for example, would be 4, because 4 goes into 12 and 4 goes into 8, and 4 is the largest number that goes into both. There are other common factors. 2 is a common factor between 12 and 8. But 4 is larger than 2. 4 is the largest. That's GCF. Well, finding the GCF of two numbers is something, it's something it could be a pain to do. Something you've done probably in high school algebra classes or whatnot. And what we're looking at now is what I want to show you now is a method of finding the greatest common factor of two numbers. And this method was actually, it's called the Euclidean algorithm, so it goes all the way back to Euclid, which is a long time ago. And before I show you all the fancy formulas of it, I just want to show you some examples with numbers. So I'm going to show you a process now. Later we'll justify the process, but I want to show you this process. It actually makes a lot of sense. So let's say I have two numbers, 51 and 21, and I want to find the GCF, the greatest common factor of those two numbers. So you take the bigger number first, you put it right over there, 51. And you see how many times does 20, basically you want to see how many times does 21 go into 51. So 51 is equal to 2 times 21 plus a remainder of 9. Now you take the 21 and you put it right there, and you say, and you want to know how many times does 9, this remainder, go into 21. So 21 is equal to 2 times 9 plus 3. Now I do the same thing. I put the 9 over here, and I see how many times does that remainder go in. So 9 is equal to 3 times 3 with no remainder. Once I get no remainder, that means this last number here, this number 3, is my GCF. So the GCF of 51 and 21 is 3, meaning 3 goes into 51 and 3 also goes into 21, right? 51 is 17 times 3, 21 is 7 times 3, and 3 is the GCF of, and this is a amazingly easy way to find GCFs. And sometimes, you may have learned other ways. I think in a typical high school class, they may say something like, take the numbers, break them down into prime factors, blah, blah, or whatever, or just figure out, I don't know what they're doing exactly, make a factor tree. But here, it's a very straightforward process. That's why it's called an algorithm. Just do this repeated division. So I'm going to give you a couple of other examples I have whipped up here. And we're going to try to find the greatest common factor of 527 and 341, which is going to be more of a task. Well, and as you can see, it's going to be a lot more steps. Or not a lot more, but some more steps. So we start with the bigger number, 527, and we see how many times does 341 go into that. In this case, it's only once. So 527 is equal to 1 times 341 plus 186. Now I take this number 341, it just goes straight down like that. And 341, how many times does 186 go into 341? 341 is equal to 1 times 186 plus the remainder of 155. Now again, I take this quotient guy here, and I take that, I want to see how many times this remainder go into that, quotient. And 186 is equal to 1 time, also happens to just going once. 1 times 155 plus 31. And now I take the 155 and the 31, bring them down here. 155 is equal to 5 times 31 with no remainder. That means that the GCF of these two numbers is 31, which means if I would take 527 divided by 31, let's just do that. 527 divided by 31, that should go unevenly. Yes, it does. Oh, 17 times 31, and 341 divided by 31. Let's see what that is. This, according to our theory, this should be a whole number, 11. So the first number is 17 times 31. The second number is 11 times 31. Clearly, the greatest common factor is 31. That was well done. Okay, let's do one more example. And here we go. And we want to find the greatest common factor of 1288 and 481. And this is not so simple to do. And this is going to take a whole bunch of steps, but we will follow this process and get down to an answer. So 1281, we say is equal to 2. Again, we want to see how many times this smaller number goes into the bigger number. 1288 is equal to 2 times 481 plus 326. 481 is, and now I take the 41 and the 326, put them down here. So 481 is 1 times 326 plus 155. Now I take the 326 and the 155 and bring them down to the next level. 326 is equal to 2 times 155 plus 60. I hope you appreciate it. I actually had to figure all these out before I, to prepare this video. I put a lot of work into it. Hope you appreciate it. I put a lot of work into these videos because I got to prepare all this stuff beforehand. Anyway, not that I'm complaining or anything. And now, let's see, 326 is, so now I take the 155 and the 16. That becomes my next line. 155 is 9 times 16 plus 11, and 16 is equal to 1 times 11 plus 5, and 11 is equal to 2 times 5 plus 1, and 5 is equal to 5 times 1. And with a 0 remainder. So again, the last non-zero remainder, the last number before I hit 0 is my GCF, which means that the GCF of 1288 and 41 is equal to 1, which means that 1288 and 481 means those two numbers are relatively prime. And to figure that out could be a big pain. Now, but I don't know if these numbers are prime numbers or not. I'm just saying that they're relatively prime, to each other. Whether they're actual prime numbers, I have no idea. Oh boy. Okay, so let's now see the theory behind this. Let's now see the theory behind. I think that was it. Let's see. Let's go and get into the theory a little bit of why this all works. Okay, so let's go back to our textbook now. Already, let m and n be two positive integers such that m is greater than n. So these are just the pair of numbers that we started with. So what I'm going to go through this process now, only now hopefully it'll make a little more sense because this is going to remind us of what we just saw, the examples that we just saw. So according to the fundamental theorem of Euclid, which I often refer to that as the division algorithm or the division theorem, we can form the set of equations that m, the number m, is equal to some quotient times the number n, because these are the two numbers we're starting with, m and n. Let me just highlight them. So these are the numbers that we're starting with here, m and n. So those numbers, so m is equal to some quotient times n plus a remainder. We're calling that remainder n1. Why n1 instead of r1? I don't know. That's what the book is calling it. But of course, n1 is less than n because it's a remainder. That's the whole point. So now I take the n and I and the n1, and I find a new quotient, some new quotient. N is equal to some new quotient times the n1, that first remainder, plus a second remainder, and of course the second remainder is less than the first remainder. This is important, by the way. That keeps on going down, 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 because like I say, it can't go down forever. It's got to stop eventually, because positive integers can't go down forever. They have to stop at some point. Now n1 is equal to second quotient times n2 plus the third remainder, dot, 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 until I get to the almost the last one, and I get n k minus 2. The k minus 2th number is quotient k minus 1 times remainder k minus 1 plus a new remainder nk. This new remainder nk, as you see, is going to be the GCF, of course. And then this last guy, nk minus 1, is equal to some final quotient times nk. And that new number nk is going to be that new number is nk, then I'm sorry, that new number nk, and let me again, I'm going to highlight the nk, so just to show this new number nk right there is going to be the GCF. So that new number, that nk number, is going to be the GCF. And that's what's saying here. And that's called the Euclidean algorithm. So the Euclidean algorithm is to keep on writing these successive sort of divisions until I get down to the bottom. And you will eventually get down to a bottom, because you can't keep on, because since all those remainders are getting smaller and smaller, and we're talking with positive integers, which are discrete. By the way, that's what discrete means in discrete mathematics. Discrete means like as opposed to continuous, or as opposed to dense. Like real numbers are dense, and continuous. Discrete is like individual, sort of separate and individual. Integers are separate and individual. Anyway, you do know, by the way, there's no area of mathematics called discrete mathematics. This course is a patchwork of different areas of math which share this commonality that they're studying discrete things as opposed to continuous or dense or whatever. Anyway, back on track. So we want to prove this theorem. That we want to prove that this last number nk is the greatest common divisor, is the GCF. Some people say GCD, GCF, same thing. And in order to prove the theorem, we're going to have to show two things. We're going to have to show that nk is a divisor, is a common divisor of m and n, my original numbers. And we also have to show that the greatest common divisor d, let's say we take the greatest common divisor, we'll just call it d, because I don't know what else to call it. And we have to show that that greatest common divisor is a divisor of nk. Once that happens, we're done. Because if nk is a common divisor of m and n, that means nk divides d. If d is a divisor of nk, then d divides nk. Well, if nk divides d and d divides nk, the two numbers must be equal to each other. That's really the whole proof. And now I'm just going to talk us through it. So here we go. So to prove so we have the two basically the book outlines the proofs beautifully. To prove the first statement, we just look at the equations. And if we go from the first to the last, so we see that nk is a divisor. Let's say first to last, nk minus 1, and using this result, we see the second member of the next to last equation is divisible by nk, and therefore it's divisible by n2. And proceeding this way step by step, we show that n1 and n2, finally n and m are divisible by nk. Let me show what does that mean. So in other words, if you look down at the bottom, nk obviously nk is times some number is equal to nk minus 1. So nk goes into nk minus 1. Well, now if we go to the next equation, nk goes into itself, and it also goes into nk minus 1. So it must go into nk minus 2. And then by the same argument, if I would go the line above, I would get nk minus 1, which is a multiple of nk, plus nk minus 2, which was shown as a multiple of nk, also is equal to nk minus 3 or whatever, which is a multiple of nk. And I keep on going up, 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 up. So I get that, I finally get, and if I just keep doing the same process, I get that nk is a multiple of n3, it's multiple of n2, therefore it's also multiple of n1. And if it's multiple of n2 and n1, then therefore it's also multiple of n. If it's multiple of n1 plus n, then it's also a multiple of m, or I'm sorry, divisor of m. So nk goes into n and it goes into m. I kept on saying they were multiple. I meant that these numbers are multiples. So m is a multiple of nk and n is a multiple, which means that nk is a common factor. Now I'm going to look at this from the other side. Let's look at the GCF. The GCF, we're calling it D. Well, D goes into M and D goes into N. So if it goes into these two guys, it has to go into the left part of the equation, because if the left side of the equation is divisible by D, the right side has to also be divisible by D, which means D has to go into N1. Well, so I know that D goes into M and N by definition, and now we've shown it also goes into N1. Well, if it goes into N and it goes into N1, by the same argument, it's going to go into N2. And then by the same argument, if it goes into N1 and N2, it's going to go into N3, all the way down the line till I get that D is going to go into NK. So I get that D goes into NK. I also established previously that NK goes into D, hence the two numbers must be the same. That is the proof. And that is the proof. Now, here is a fascinating, fabulous corollary of the proof. Every common divisor of M and N is also a factor of the greatest common divisor. That follows. And here's a second theorem, that any number ni of the above set of equations is the difference of multiples of M and N, which is also a really interesting fact, and we're going to use that in a second. We're going to use that to find. We're going to use that to find. We're going to use this fact for theorem 3. That's really the crown here. That if D is the greatest common divisor of the positive integers M and N, then there exists positive integers alpha and beta such that alpha M minus beta N is equal to plus or minus D. I don't know why you have to have a minus there, but that's what they have. I don't know. Anyway, because it says, no, I don't get it. Anyway, that is the story. That is the story. So what I'm going to do now for the rest of this lecture is to show you how to use the Euclidean algorithm, how to use the Euclidean algorithm, not only to find the greatest common divisor, which we did already, but we're going to use the Euclidean algorithm to express that greatest common divisor as a linear combination of the two original numbers. So let's go back, excuse me, let's go back to our, okay, let's go back right here. And I actually typed it here already, but it's hidden from view. Here we go. Yep. Okay, let me just make it so we can see it better. Let's make this. So we start on the bottom 3. We start with the bottom number 3. 3 is equal to 21 minus 2 times 9. So 3 is equal to 21 minus 2 times 9. Now for this 9 here, I'm going to substitute for 9. And for my next equation, 9 is equal to 51 minus 2 times 21. So for 9, I'm going to substitute 51 minus 2 times 21. That's where that's coming from. And now I'm just going to rearrange everything, just bring out the 51s and the 21s. I'm really done. 3 is equal to negative 2 times 51, because I get that from here, and plus 5 times 21, because that's 21 minus 2 times minus 2, that's plus 4. So that's 1 plus 4 is 5. 3 is equal to negative 2 times 51 plus 5 times 21. So I've expressed the number 3 as a linear combination of my original numbers, 51 and 21. Let's just check this out. Not that you want to trust me or anything, but let's see, 5 times 21, 5 times 21 minus 2 times 51, 2 times 51. And look at that, equals 3. Isn't that awesome? So that's how we do that. So I've used the Euclidean algorithm to express the greatest common factor as a linear combination of my 2 original numbers. And again, this is an algorithm. Why is it called an algorithm? Because an algorithm is something you can just follow the steps, plug in, and get and crunch out your answer. Let's see if we could express 31 as a linear combination of 527 and 341. Not so simple to do. If I would just say express 31 as a linear combination, some integer times 521 plus some integer times 341 equals 31. That's not so simple to do that. But for us, it's going to be very simple because we're smart. Oops. Obviously not that smart. Okay, here we go. So here we go. So let's just okay. So what we do here is, let me just get it on the same. Okay. So I start again from this bottom line here, the last remainder, 31. So 31 is 186 minus 155. 31 is 186 minus 155. And for the 155, I'm going to substitute in 155 is 341 minus 186. I mean, again, I just keep doing these substitutions. So for the 155 here, I substitute this little parentheses. And now I just combine common terms. I'm not just multiplying numbers out because I want to keep these quotient numbers separate. So this is -1 times 341, and that's 186 really plus another 186. That's 2 times 186. Now for this 186 guy over here, that 186 guy, I'm going to substitute because 186 I see up here is equal to 527 minus 341. So for the 186, I'm substituting 527 minus 341. And I combine like terms, so to speak. I get 2 times 527, that goes right here. I get -1 minus 2, so it's -3 times 341. And this is the story. So let's see if this works. I mean, I'm showing you all these fancy steps. Well, let's just check it out, see if it actually works. That's why, you never believe anything I tell you. So I'm going to do 2 times 527, 2. You know what they say, if you listen to everything I tell you, you'll become a good mathematician. If you don't believe anything I tell you, you'll become a great mathematician, meaning you'll work it out for yourself. 341. Okay, drum roll, please. 2 times 527 minus 3 times 341 equals 31. Is that nice? 31, by the way, that's Baskin Robbins. Just thought I'd say that. Alrighty, so that is wonderful. That worked. That worked beautifully. And now for the big one, what we want to do now is we want to express 400. We want to express the number 1, which is the greatest common factor. We want to express the number 1 as a linear combination of 1288 and 487. That's not so simple to do. That is not so simple to do. Well, let's see if we could do that. Okay, so I do have this here. Let me. Let's see, where is it? See these tricky things they do here. Okay, let's go through it step by step. I don't think I can fit it all on one page, so I'm gonna have to make it smaller now just so we can see it. I hope you can all see this here. Okay, so I start from the bottom here. 1 is equal to 11 minus 2 times 5, which is what I put over here. And for the 5, I substitute 5 is equal to 16 minus 11, which I get from there. I work it all, I multiply it all out. I get that's 1 is equal to negative 2 times 16 plus 3 times. But at any time, if you would check these out, you'd see they'd work. For example, this here is 33 minus 32, and that gives me 1. Anyway, for 11, I substitute based on this line up here. I get 11 is 155 minus 9 times 16. Get rid of the parentheses. I get 3 times 155 minus 29 times 16. And now I substitute 16 based on this line is equal to 326 minus 2 times 155, which brings it down here. I, again, multiply out the parentheses, and I have 1 is equal to negative 29 times 326 plus 61 times 155. And again, if you would work that out, you'd see that would also work. I'm going to test out the bottom one. I'm not going to test each one on the way. You can do that if you want. Now for 155, I substitute from the next line 41 minus 326, 41 minus 326 for my 155. Now multiply out all the parentheses, and I get this guy here. And now I have a 326 right over here, which I use that. I substitute for the 326. I substitute based on this guy, 128 minus 2 times 41. And now I just multiply out parentheses, and I get my final answer that 1 is equal to negative 90 times 1288 plus 24 plus 241 times 481. And let's see if this actually works. So let's do 241. I just like doing the positive ones first. 241, so I'm so positive, times 481, 481, and then minus 90. That's a big 115,000. That's a big number. Times 1288. And so 241 times 481 minus 90, and drum roll please. Yes, it equals 1. So I've expressed the number 1 as a linear combination of my original numbers, 1288 and 481. Another way of saying that, instead of saying I'm expressing it as a limited, I could say I'm expressing it as a linear combination. I could also say that I found an integer solution. I could say that if I look at the equation 1288 x plus what was the original numbers again? 481, 481 y. So I could say I have. So I could say that the ordered pair let's see, negative 90 comma 241 is an integral, is an integer. I don't mean integral like calculus integral. I mean integral like an integer. Is an integral solution. See, we know that if I have the equation 1288x plus 481y equals 1, we know that's an equation with an infinite number of solutions. But to find solutions that are where x and y are both integers, that is not so easy to do, except now we've done it. So you could say that I've expressed the GCF1 as a linear combination of 1288 and 41, or another way you could say the same thing is that we found an integral solution of this equation. By the way, they call these kind of equations, they call these Diophantine equations. So when you have an equation with whatever many variables, and you're looking specifically for integral solutions. And when I say integral, I don't mean integral like a calculus integral. I mean integral like an integer, integer solutions. They call it, not that it's important. I'm just saying they call it that. Well, this really, I believe this really is what I wanted to do today. Yes, we're in good shape. Yay for us. This is the end of this video, and we'll see you guys next time. Hope you enjoyed the Euclidean algorithm of 1.9. I loved it. Bye, everybody. See you next time.